Hi everyone, I'm very glad to be able to present our work on Clonos, an approach to consistent causal recovery for highly available streaming data flows. This is work done together with my colleagues Marius Frakulis, Diomedes Spinelis and Asterios Katsifodimos at the TU Delft. Stream processing systems were initially designed for low latency analytics, but more and more we see them being used in critical use cases such as stock trading, fraud detection, and in general for building reactive low latency applications. Now, these new use cases introduce a new set of requirements on these systems. While analytics only require the performance system with localized state, financial applications additionally require that this state is consistent in the sense that each input message should be reflected exactly once in the state of the system. Critical applications additionally require high availability because downtime is often equivalent to revenue loss. And finally, all these more complex use cases require non-determinism in order to be expressed. And I want to dig a little deeper into why that is. Non-deterministic computation is a computation which depends on factors other than initial state or input. And a good example of that is obtaining the correct time. You call it with the same parameters every time, in this case none, and you get different results every single time. And in stream processing, non-determinism can be present in the functions that users define, but also in many of the essential system level components. Let me illustrate this with an example on fraud detection. Say you're at the supermarket and you buy something. This transaction is going to be sent to a queue such as Kafka and later ingested into a data flow which is going to attempt to validate that transaction. In stream processing, the computation is static, but the data is transformed by flowing through the operators. Now, to actually implement this, you need to timestamp your records at the source operator and emit watermarks, because the timestamps from the point of sale systems may not be reliable. You may need to contact an external database in order to enrich your data, and you may need timers to power your windows. Finally, you also need to shuffle data around, leading to operators with multiple inputs. And what these highlighted features have in common is that they are all non-deterministic. And there are many more examples of non-determinism in stream processing. Non-determinism is exactly what gives us the ability to express these complex use cases. Now back to the requirements laid out earlier, I want to describe two classes of systems as to how well they support them. There are systems which perform global recovery and systems that perform local recovery. And first we're going to talk about the global recovery systems such as Apache Flink, Heron, or Jet. This class of systems often uses external storage, such as HDFS, to maintain a set of consistent checkpoints. These consistent checkpoints are taken by flowing a barrier through the system which trigger a local checkpoint. Upon a failure being detected, the entire computation must be halted, the failed node is substituted, and every node then must reload its previous global state to restore consistency. This process of rolling back state allows them to support non-determinism extremely well, but it means that it has fairly slow recovery, which gets worse on larger graphs. And because of this stop-the-world kind of recovery, these systems cannot be highly available. Next, let's talk about the local recovery systems, which attempt to address the cost of global recovery by only applying treatment at the failed operators. To explain local recovery, let's take the failure of this node as an example. The first strategy I'm going to tell you about is called pure local recovery, and that is where we're going to schedule a substitute for the failed operator only after the failure and attach it to the graph. You then also need to load a checkpoint of the operator state. And because you're restarting this node from a prior checkpoint, you also need to do two things. First, this node must reprocess all lost inputs since the checkpoint, and two, you must deduplicate any outputs you've already sent. You can accelerate this, for example, through passive standby, and in passive standby you're going to maintain a shadow operator for every main operator with the latest checkpoint already prepared. This way you don't have to wait for loading the checkpoint. Whenever a checkpoint completes, you transfer over the new state. That way, after a failure, you can immediately substitute the operator, but you still need to reprocess the lost inputs. And now, hopefully you can see the problem, which is we have two incarnations of each operator running non-deterministic operations over the same data, and that of course is going to lead to inconsistency. And all of these strategies have this same problem, because of course all of them have two incarnations, one before failure and one after failure. Thus, in prior work, you always need to choose between consistency and non-determinism if you're doing local recovery. If you choose non-determinism, you of course lose consistency, and if you choose consistency, you cannot use any of the functionalities that I've shown before. This means you could not use ingestion time, you could not contact external systems, or use timers. There are still the need to address shuffles, and what many of these systems do is that they sort deterministically all inputs, leading to a higher latency overall. And so our research goal was to design a local recovery scheme with support for non-determinism and exactly once consistency, and with minimum degradation of performance. And Clonos has been the result of that. We built Clonos through the re-engineering of Apache Flink's distributed runtime. The key insight in Clonos comes from rollback recovery, and that is that instead of forbidding non-determinism, we can instead log all of the non-deterministic operations. For example, if this operator here processes this purple record first, then it writes that down into the log. And if it processes, this is what's called a determinant. If it processes the green record next, then it writes that down into the log. This approach also works with other non-determinism, like time and contacting external systems. If a failure does happen, the recovery node, the second incarnation, will need to know how to re-execute these operations in the exact same order. It can do this by first obtaining a copy of the log and using it to guide its recovery. It begins processing, and whenever it is going to execute a non-deterministic action, it consults the log and executes the action there. Same for the second record, and similarly for timestamps or contacting external systems. And so our contributions are as follows. We propose logging as an efficient remedy to the tension between non-determinism, local recovery, and exactly once consistency. We present Clonos, a fault tolerance approach combining checkpointing, standby operators, and a specific kind of logging called causal logging. In the paper, we also present an analysis of non-determinism in stream processing and a proof sketch of how Clonos can guarantee exactly once correctness. Finally, we are going to present a set of empirical experiments in realistic deployments. So our first challenge here was actually choosing a logging protocol. If we were to use pessimistic logging, such as done in databases, every vertex in our Dataflow graph would need to synchronously write every non-deterministic operation it does to external stable storage, receive a response before actually emitting records, and this would have far too much latency. Optimistic logging is better in terms of performance because it allows operations to be batched, and then it can write out a log entry asynchronously. And so an operator can process a very large set of records and only later write it out. The issue is that after a failure, there is no guarantee that the full log will be available. But there is a third option, somewhat unknown, called causal logging. And causal logging is very appealing in a stream processing setting because an external system is not needed. Instead, the log is kept entirely in volatile memory in the system. The catch is that the log must be shared with all causally dependent nodes, and that is the downstream nodes, as shown here. After a failure, we can then obtain the log from the downstream nodes and use it to restore consistency. And so, at a very high level, during normal operation, Clonos does just the following. We use passive standbys and perform state snapshot dispatch after every checkpoint. Alternatively, you can also just do pure local recovery. We also do in-flight logging, and what this means is that whenever a record is sent downstream, a copy is kept locally until it is no longer needed. The final piece here is causal logging. Each operator has a causal log, which is shared with all of its downstreams. I'll draw just two here, the gray one and this pink one. Replication is going to be happening incrementally, and so whenever we want to send a record, such as this green one, we're going to piggyback on it all of the necessary log deltas needed to reconstruct that precise record. And before processing it, the receiving node must first copy all of those determinants, all of those log deltas, over to its local copy of the logs. In response to a failure, Clonos is then going to execute a 6-step protocol. The first thing to do is to activate the standby node. Then, we reconfigure the network connections to connect this new node to the data flow. Next, we're going to retrieve the log copies from downstream and keep only the most complete version of the log. Concurrently to the previous step, we can request the replay of all in-flight logs from the upstream nodes. That is, they're going to replay all of the records since the last checkpoint. Finally, we can use the log and the in-flight records as shown before to replay the exact execution of the first incarnation of the failed operator, thus reaching the last observed state of this operator. The only thing left to do is to deduplicate the resulting records of this recovering node. And to understand the duplication, we're going to focus on this connection between the decide and the reject node. So here I'm showing a few more runtime details of the decide operator. The duplication is happening at the same time as the operator itself recovers, and so the records which are emitted are being serialized into buffers. And normally, these buffers would stay in the output queue until they are sent into the network down to the reject node. But since this buffer contains duplicate records, we need to deduplicate it. And we do that by moving it into the in-flight log. This way, we are both deduplicating and rebuilding the in-flight log at the same time, meaning that we can support future downstream failures. But how do we actually know that we must move this buffer to the in-flight log? Well, we can ask the downstream node how many buffers it has received and what sizes they were. Our trick here is to also track this as a causal log just for the network channels. Thus, according to this example here, when the next buffer has exactly 27,680 bytes, let's say that's this amount here, we must finalize it and move it into the in-flight log, thus deduplicating it. Okay, now that we understand the high-level protocol, you may ask if this isn't quite expensive. For example, the gray log of the source node would need to be shared with all of its causally dependent nodes, meaning all other nodes, and the log of this enriched node as well, and the log of the other enriched node as well. And so you may ask, well, isn't this getting out of hand quite quickly? But if we define this determinant sharing parameter, in case you want to trade off guarantees for performance, at a determinant sharing depth of 1, a log will only be shared with its direct neighbors of a node as shown by the dashed lines. Thus, in a very large graph, we would replicate considerably fewer logs. This deployment can still handle a large number of simultaneous failures, such as shown here, because all logs can still be found in the downstreams from the failure. However, we cannot handle a sequence of failures larger than the determinant sharing depth, such as this one. To deal with this, Clonos will automatically detect these pessimistic rare cases and trigger a global rollback in order to restore consistency. Now, users, of course, do not need to be aware of any of this. They only have contact with an abstraction that we call causal services. We offer built-in causal services for timestamps, timers, HTTP requests, and random numbers, and more. These services implement some very simple logic to either generate a new non-deterministic value and log it into the log, if in normal operation, or to read one value from the log if we're recovering. Users can also register their own causal services by providing a function that returns a serializable determinant. Switching a Flake workload to Clonos is thus very simple, as users need only change non-deterministic calls, such as system current time millis, to the service equivalent in order to capture that non-determinism. In the paper, we also outline many design decisions and optimizations which make Clonos a reliable and performant system, such as efficient designs for causal services, tracking at the level of buffers instead of records, and allowing the in-flight log to be spilled in order to recycle memory. But for now, I would like to move on to evaluation. We evaluated Clonos using Kubernetes on the Surf-Sara cluster. We compare Clonos to Flink, the system we modified. Thus, we deploy both systems under test on Kubernetes, as well as HDFS for storing checkpoints. We analyze both the failure-free performance overhead introduced by Clonos and the recovery performance. And we use two different workloads for this: the Nextmark benchmark, as implemented in Apache Beam, and the synthetic job, which gives us much more control over the shapes of the graph. For failure-free experiments, we simply submit the jobs and measure throughput and latency from the metrics. For recovery experiments, we wanted to measure realistic end-to-end latency and throughput. Thus, we also use a Kafka cluster with input and output topics as well as load generators, set at 50% of the maximum throughput these systems can handle. End-to-end latency is then measured from the load generators to a response in the output topic, and throughput is going to be sampled at the output Kafka topic as well. We ran the full Nextmark benchmark, plus the extra queries defined by Apache Beam's implementation at a parallelism of 25. The queries vary in depth between 1 and 6 tasks with dozens of operators. In total, the queries vary between 25 and 150 hosts. We observed that full determinant sharing suffers an average throughput degradation of 7%, while the determinant sharing depth of only 1 suffers a smaller 5% average degradation. We owe this low overhead to the ability to perform all of those logging operations in memory due to our choice to use causal logging. The worst cases here are queries 5 and 7, where this goes up to 26 and 16% respectively, and that is because these are the deepest graphs where the overhead of determinant sharing was highest. All in all, we are happy with these results and believe that there is still room for further optimization. We also performed failure experiments using those same Nextmark queries. Query 3 here simulates item suggestion by looking at items purchased in states close to the target user. It performs filtering, selection, and full history join. Here I'm going to show throughput over time in blue for Clonos and in red for Flink. The dashed vertical line indicates where a failure was introduced. Note how, even in a query with relatively small state, Flink suffers a large period of downtime, while on the other hand Clonos maintains strong throughput throughout. This is because in Clonos, while local recovery is happening, the rest of the graph is able to keep processing. If we look at latency over time, we see that Clonos reaches the pre-failure latency 9 times faster than Flink. Only a very small number of records is emitted with high latency, as these records were waiting in queues while the operator replayed through its inputs. On the other hand, in Flink, all partitions must recover separately and slowly. The last experiment I want to show you uses our synthetic pass-through query to push these systems close to their limits. In these experiments, we fail 3 connected tasks. In the first one, we're going to fail a task every 5 seconds. Notice how Clonos never blocks and quickly returns to the original set throughput of 250,000 records per second. Regarding latency, notice how the large majority of records in Clonos are still emitted at millisecond latency even while the system recovers. In the second experiment, we're going to fail all 3 tasks at the same time. And even here, Clonos' decentralized recovery protocol is able to quickly restore consistency. The takeaway being, even in difficult failure cases, Clonos is able to quickly recover a consistent state through only localized operations. In conclusion, with Clonos, we improve on previous highly available stream processing systems by adding back the support for needed non-determinism, making it as expressive a system as Flink. We also made a configurable system in terms of its guarantees and overhead, and in the paper we describe how Clonos can also be used to achieve at most once or at least once semantics. Finally, we made it practical for users by offering needed features such as causal services and the reliability of a spillable in-flight log. You can find more details in our website below or in the paper. Thank you for your attention.